So it's this one. If you actually got this one correct and you're sitting in front of your homework, you can go to sleep for 5 minutes. So to compute the principal stresses, those are the eigenvalues, and the eigenvalue problem is that the determinant of sigma minus lambda I is equal to 0, and we're going to solve for the sigmas, okay? So the first thing we'll do is write down sigma minus lambda I, so we'll rewrite sigma. And I'm going to go kind of slow and explicit step by step. I'm recording this and I'll post it so you can go back if you don't understand. So that's sigma minus lambda I is just the identity matrix. All right. That's equal to 18 minus lambda, 0, 24, 0, minus 50 minus lambda. Okay, and so then we want to take the determinant of this thing, set it equal to 0. So remember how I told you to you could take the determinant by taking this term and multiplying by the determinant of that guy, right? So and then we would do this times the determinant of that, but it's 0, so we'll skip that. And that would be a minus sign in front of it if it wasn't. Right? So it would be minus this times the determinant of that, but it's 0. So then we have the last one is this times the determinant of this. So 24 all right, and that's equal to 0. Yes. So then you have 18 minus lambda minus 50 minus lambda, 32 minus lambda minus 24 squared minus 50. Okay, so you could multiply that all out and then solve the quadratic equation, right? Using, well, actually it's a cubic equation. So you could multiply it all out and then factor it or whatever. Does anybody know how to solve this really simply? How about stick it in your TI-89? Or, you could do it, but it's okay to use a computer or whatever, right? And if you do, these are your 3 eigenvalues, or in the context of stress, that's your principal stresses, right? They are pretty straightforward. I mean, it wouldn't be that hard if you multiplied this out. I think you could factor it just by eye. It's not going to be that, yeah. Well, you don't know. No. You'll know the directions we're about to solve for them. They're the eigenvectors. Let's solve for it, and you'll see. All right. So those are the magnitudes. Okay. So for lambda equal to 50, then we want to solve, the equation sigma minus lambda I v equals to 0 vector. Okay, we're going to solve that for v. Okay, so we're going to plug in 50 for lambda. So we have 18 minus 50, 0, 24, 0, minus 100, 0, 24, 32 minus 50. That's equal to minus 32, 0, 24, 0, minus 100, 0. All right. And of course, if we augment this with 0, 0, 0, this is the system of equations we're trying to solve. And I think some of you just tried to maybe plug this system of equations into your TI-89 and then do solve. And I don't really know what it does there because there's an infinite number of solutions. I'd have to go and look at it. I don't know off the top of my head what it does. I haven't used a calculator in ages, like a hand calculator. But I think there's a function in your, if you have a TI-89 or the HP equivalent, engineering calculator, there should be a function called RREF, where you put the matrix in here. So this would be the matrix that you put in there. What RREF stands for is reduced row echelon form. And that's what we're doing when we do these matrix operations. We're putting it in reduced row echelon form. So whether the linear solve or the solve equation thing works or not, I'm not sure. But I know RREF will work. If you put the matrix in right here, and you run this function RREF, then you'll get what we're looking for, and you'll be able to write down the solution then. So okay, but anyway, this is not that hard. So I'm going to kind of do well. I'll do one at a time because I think this is where a lot of people got confused. All right, I'm going to take 1/24 of row 3. Okay. So I have. So I have 1, 0, minus 3/4. Right? 0 minus 100, 0 minus 32, 0, 24. Okay? So at this time I'm going to do 2 of them at once, okay? I'm going to do 1/32 of row 1 and minus 1/100th of row 2. All right. So then I have minus 1, 0, 3/4, 0, 1, 0, 1, 0, minus 3/4. Okay? So now you see that rows 1 and 3 are not linear, they're not linearly independent of one another. That's what we say, right? I can you can see if I multiplied by minus 1, they'd be the same exact row, right? But I'm going to leave them like that so I can just add them together. So now I'm going to add row 1 to row 3 That's going to be my new row 3. All right, so then I have minus 1, 0, 3/4, 0, 1, 0, 0, 0, 0. Okay, so now I can write down the so now I have x1 equals to 3/4 x3, x2 is equal to 0, and x3 is free. Okay? Now, you could choose one, and that's typically what you do, but I don't like fractions. So I'm going to choose x3 to be 4, right? And then when I plug that in up here, then I have 3. So then I have 3, 0, 4. So V1 is equal to 3, 0, 4. Okay, it's also equal to 3/4, 0, 1. If I would have chosen, everybody see that these are in the same direction? These two vectors are in the same direction. They have a different magnitude, but they're in the same direction. All right. But when these eigenvectors, all we're concerned with is the direction. Okay? So you asked about my little cube, right?
Yeah.
All right. So if we wanted to draw that, okay, we would so if this is my Cartesian space, then I have a vector that's, let's see, this is x1, x2, x3. So I have a vector that is 1, 2, 3 in the x1 and 4 in the x3. 1, 2, 3, 4. So it'd be somewhere over here, okay? And it's in that plane. So this is my vector, okay? This is my eigenvector, right? So then that little cube, or little stress cube, would be oriented such that one of the faces, and I don't know if I can draw this correctly, but no, that's not right. Well, of course. Awesome. I love Microsoft. Anyway. So yeah, so that direction, one of the faces of the cube would be normal to that direction, okay? And then the traction vector acting on that face, normal, would be of magnitude 50, because that was the eigenvalue. So the normal stress to that face, defined by the direction, would be 50. Okay? So that's just one vector. There's two more to solve for. And we just follow the same procedure. You know, it's very step by step. It's not really tricky at all. I mean, you just plug in the eigenvalue and perform the row operations, and that's it.